Hi, so there was one more thing about hypothesis testing we needed to talk about. Now, nothing new conceptually is going to take place in this video, in the sense that the methodology behind hypothesis testing and the philosophy behind it and the reasoning we use going forward to conduct it, those are going to remain constant throughout this class and in the future. The basic idea that we assume a null hypothesis, that we can't make the claims that we would like to make, and then show evidence to sort of disprove the null hypothesis is always going to be the way we conduct this business. But there are some types of hypothesis testing questions that get a little bit technical, and it's worth talking about that technicality and how to resolve it. We don't use any conceptual tools that we haven't already covered in this class. So let's say there are two different types of microelephants. On the one hand, well, you know what? I'm going to use purple because we've been talking about purple microelephants this whole time. On the other hand, we're going to have blue microelephants. And let me give a little bit of space down here. Our researcher has come to ask herself the question, do they weigh the same? Same on average. And you can imagine how a question like this generalizes to all sorts of situations, right? Like, let's say you have people trying two different types of diets. A special diet that some researcher claims to give XYZ health benefits, and then a bunch of people eating their regular dietary routine. And you can ask whether or not one of these groups in fact performs better on the proposed metrics than the other. Or you could have, two different classes who were taught in two different styles, and you want to know if like the test results turn out better for one class or another, or if there's any difference. And so you can imagine that uh, this sort of thing comes up a lot, right? And so, unlike the previous hypothesis testing questions that we've done, where we uh, have some number that we're comparing a population mean to, instead we're going to compare two population means to each other. So in this case, we have the purple microelephants and the blue microelephants. And what we want to know is how do their means compare to each other. Now, we've already been over this, so of course there's no way to actually know this without measuring every single elephant on Earth, and we can't do that, so we need an alpha value or significance level, and let's go with the standard 5% for now. Alright, now, as usual, the second step is going to be to go out and weigh yourselves a bunch of elephants. And so we're going to weigh, let's say you get your hands on 40 purple microelephants, and they have average, say, mean of P is, let's stick with the same numbers we've been using. Why not? So let's say they have a mean of 125 pounds and standard deviation of 20 pounds. And then you go weigh some blue microelephants. Let's say you can only find 35 of them, and their average weight is 125. And let's say their standard deviation is 10. Right? So let's see what that looks like. So purple microelephants are uh, they have a weight with some sort of distribution, right? And as usual, when you weigh a bunch of those things and take your average weight, the sampling distribution converges to normality as your n gets big enough. So having weighed 40 elephants, we can safely assume that that curve is normal. So the distribution of the sampling variable, of course, is some sort of normal curve where the standard error for purple microelephants is 20 over square root of 40. Now, of course, the whole point is that we don't actually know the mean, right? We don't know what the actual average weight of purple microelephants here is. So I have an example of a curve, but it could be something like that. It could be something like that, right? And then with blue microelephants, they too, right, are a normal distribution. Uh, and their standard error for the blue microelephants is 10 over square root of 35, right? Because their n was 35 and there was, and the measured deviation was 10. But, as usual, the we don't know the mean, right, of the weights of the blue microelephants. So there's a lot of different normal curves that could be. And what we're trying to see is uh, how likely is it that they have the same mean, and whether or not them having the same mean could explain results like what we see here. So this gets pretty complicated if we're looking at two different random variables uh, with two different possible means going all over the place. And so what we would like to do is reduce this down to be talking about one random variable. So let's talk about two different random variables here. Random variable one, let's call this random variable x bar 35p, right? And this is going to be average weight of, sorry, we weighed 40 at the purple microelephant, sorry. 40 purple microelephants. It's normal. Mean is who knows. Standard deviation is what we already said. I'm going to skip the 40 just because it's too ugly to write that over and over again. The standard, and then the standard error is, what do we say? It was 20 over square root of 40, right? And then we have our blue microelephants. And their average weight of 35 BMEs. It's also normal. Its average weight is who knows. And our standard error for the blues is again 10 over square root of 35, right? And so far, this is just writing down exactly what we've drawn here. Oops, right? And we've just sort of formalized it. But now this is the pulling the sort of rabbit out of the hat moment, I'm going to define a new random variable xd, and the d stands for difference. I'm going to define xd to be xp minus xb. So this is this thing right here is going to be the difference, right, of the two random variables we already defined, the weights of xp, or the weights of the purple microelephants minus the weights of the blue microelephants. So it's also a random variable. And so let's see what we know about this random variable. Mu of xd is mu of xp, minus mu of xb. Of course, we don't know what either of those things are, right? But that's okay. There is some average, and there is some average, so this average exists, right? The variance of xd, and just to make things go faster, I'm going to stick to black, I think. The variance of xd is going to be the variance of xp minus the variance of xb, plus the variance of xb, right? And this goes back to chapter 2 and those, the linear combinations of random variables, right? So I have two variables, both with some sort of variation. When I take their difference, I'm compounding the variations, so I add their variances, and hey, we know what those variances are, because we know the standard deviations are 20 over root 40 and 10 over root 30 respectively. And so I know that the variances are the standard deviation squared, so it's 20 squared over 40 plus 10 squared over 35. And I can work out what that is, but I can just throw that into a calculator, so I'm not going to stress about it too much at this moment. And then finally, the last piece of this then is the standard deviation of xd. What should that be? Well, it should be the square root of the variance, right? That's what we've shown before. So we can go ahead and do that. So we have this new random variable, which is just take take these two samples and subtract their means. And both of the samples can have different means when I sample them. So they're both random variables, their difference is a random variable, and here are some of its parameters. Its mean is who knows, its standard deviation is going to be that expression. And so we should note in general that if you just had let's say an x1 whose mean you didn't know, how do I want to say this? Let's say you had a random variable x1 and we knew that its sample standard deviation was just s1. and it had size n1, and you had variable x2 with parameters standard deviation s2 size n2, then if you had xd for the difference, its standard deviation is going to be the square root of s1 squared over n1 plus s2 squared over n2, right? And that's just following the same arguments that we made here. We said, all right, that's the variance of the first variable, that's the variance of the second variable. So this would be the variance of the first variable, this is the variance of the second variable. Take your sum, take your square root, right? And this is important because what we're going to do now is, oh wait, we're not quite there yet. What we're going to do now is say, hey, look, going back to the original question as to whether or not they weigh the same, we need to know an alternative hypothesis, right? And we could have defined some weird known alternative hypothesis on the two different variables, but now that I've combined them into one variable, I can say, hey, I know what's going on. My alternative hypothesis is that mu xd is not 0. And what that means is that my null hypothesis is that mu xd is 0. Right? And then what's my point estimate? My actual point estimate then is, well, it is the observed mean from the first of my two random variables minus the observed mean of my second random variable, and in this case that's just 125 minus 136, which is minus 11, right? I've noticed a negative 11 pound difference, right? That's what we saw. And so, as usual, just like we did before, what's going to happen is we're going to assume the null hypothesis, right? That the difference is 0. And then we're going to look at a curve. We're going to notice, let's see what color I want, the minus 11 out here. And we're going to want to know, all right, how likely is something like that? How likely is it that we observe an actual point estimate that is that extreme or that far away from 0? And so we got to remind ourselves what the standard deviation of this particular curve is. And so remember, the standard deviation of xd is, in fact, in this case, square root of, the hell is it again? 20 squared over 40 plus 10 squared over 35. All right, so let's get to work. Now that we have all this, it's pretty straightforward to compute that. And so normal, da 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 da. So again, our mean is 0. Our standard deviation is square root 20 squared over 40 plus 10 squared over 35. And we want to know the, let's say, Let's say the probability that's more than 11. So here's 11. Let's go from 11 to a million. Right, that would give me the rightmost tail. And that gives you a p-value of 0.001078375. And 0.001078. Let's just go with that. That's pretty far up. And then we have to multiply by 2 because, again, there's 2 tails here, right? And that gives you a value of about 0.002156. On the other hand, I could try to figure out what this area here is, and if I take out that area, then all I have left is the tails. So if I do that, I'm going from minus 11 to 11. Give it a second here. All right, there we go. 0.99784. So 1 minus 0.99784, 0.00216. So pretty much the same thing. If I go out one more, it's 4.3. Yeah, that's almost exactly the same value. Okay. So my p-value is, sorry, so my p-value is 0.002156. And that's definitely less than 0.05, which is what we said alpha was. Right. And so, in general, if you had a variable x1 whose average value was x bar, you had a standard sample standard deviation and a mean, and you had an x2 with its own average value, standard deviation, and mean. So that's kind of misleading. Oops. Then the differences is going to be the differences in the sampling variables. It's going to have as a standard deviation uh, S1 squared over N1 plus S2 squared over N2. You'll have an alternative hypothesis, which is that the mu of your distribution is greater than, less than, or not equal to some value, which I'm going to call mu naught, mu d, separate from mu naught. The null hypothesis is that your differences is going to be mu naught. In our previous example here, mu naught was 0. And what we'll have then is mu naught. Somewhere over here, our point estimate. The point estimate is just the difference in the observed sample means, and that goes inside here somewhere. And then from there we compute everything the same as if we were doing the one variable case. All right, and then of course there is a calculator already to do the one variable hypothesis testing. So it shouldn't really surprise us that there is a calculator to perform the two variable hypothesis testing as well. What we would do, of course, is enter in our parameters. So for the purple microelephants, there are 40 of them. They weighed 125 pounds on average. They had standard deviation 20 pounds. The 30 blue microelephants had average weight 136, standard deviation 10 pounds. And we were wondering if their difference was 0 with alpha 0.05. So the alternative hypothesis is that the difference between the weights of the two elephants is not 0. And when we go ahead and run that, we see that this minus 11 is in the rejection zone. We have our p-value. And so what this is telling us is that if blue and purple microelephants weigh the same, there's like a 0.2% chance we would see results like the observations we initially made. It's much more likely that they in fact don't weigh the same because of how unlikely something like this is. So hopefully this helps clarify how we should think about the two variable hypothesis testing question. To sort of recap it all together, we have two random variables. Sampling the two random variables themselves gives you two different sampling variables. Taking the difference between the two sampling variables gives you a difference variable, which is also normal. And our goal then is, what we do then is describe a null and alternative hypothesis based on the difference variable, and then we do all the hypothesizing testing stuff with respect to that difference variable. And the parameters of the difference variable are things we figured out how to compute from chapter 2, so we know exactly how they behave. So hopefully that clarifies that, and we'll talk to you guys later.